Hello everybody, Arlington Matrix here, and today we're going to be just taking a quick look at the spring mass damper dynamic response. This is one of the first problems that you'll encounter when taking anything like control theory or applications for differential equations, so I figure it's probably a pretty comprehensive video to start here. And not only that, it also contains some mechanics which should be helpful in your studies, depending on whether you're at college, university, or what have you. So let's get started with this. We're going to be taking a look at this basic spring mass damper system. Now right here, this is essentially our ground. We're going to define that with variable u because in general, when you're going to be solving this problem, you're going to need some kind of input. Basically, in this case, our input's going to be static, but we're going to have some kind of input. We're going to call it u, which basically, that's going to be our ground right here. About this y naught is basically our equilibrium point. I'll call that EQ. So basically we have our displacement of the mass, which is going to be x, that is relative to the equilibrium point, and that's going to be important to note later on. And basically we have a regular spring here where the force in the spring is equal to k times the extension of the spring. I'm going to call that xs. And we have a linear damper, call that FD, which is going to be, that's going to have a force in it that is equivalent to some C constant, damping coefficient, multiplied by, we'll call it X dot S. And those X's don't directly relate to this yet, but I will explain that later on. So basically in this problem, what we're going to be taking a look at is the dynamic response of this system under a few different loading conditions. First, we're going to be deriving a representation of the dynamic system. And that's basically going to be either a transfer function or a state space representation of the system. Then we're going to be taking a look at a few different cases for the stability of the system. And finally, we're going to put some numbers to it. And we're going to be finding the values of the natural frequency of the system, omega n. That'll be the natural frequency that the system responds to. So if there's a sudden disturbance or any kind of disturbance to the system, then as it returns to its steady state or its equilibrium state, it's going to be responding in an oscillatory way with frequency omega n. If it is an oscillatory response, which we will discuss later on, we're going to be taking a look at the damping coefficient, and we're also going to be taking a look at trying to find x as a function of t. If there's an initial disturbance, what is the actual function, or what is the actual dynamic response going to look like when plotted against time? So let's get started with this. We're going to start with our equations of motion. So first we're going to draw our free body diagram, and we're going to equate that to our mass acceleration diagram. So for the free body diagram, one thing we're always going to have, as long as this is acting in the y direction here, we're going to have gravity. We'll just call that Fg, force of gravity for now. And we have to kind of make some decisions here about how this is going to be analyzed. What we're going to be looking at here is our x direction is from here and up. So our positive direction is going to be upwards. Find that as our positive direction. And if the x displacement is in the positive direction, then the spring is going to be under tension. Therefore, our force of the spring is going to be acting down here in the negative direction. And if we have a positive x velocity, the damper is going to be resisting that velocity, so once again we're going to be having a force that is acting in the downwards direction. Call that Fd for damper. And looking at the system, there's no other forces that we need to include there, so let's draw our mass acceleration diagram. The mass acceleration diagram is basically just showing the result of these forces. What are these forces actually doing to the body. If there was any kind of rotation, then we would have to include a moment in there. But in this case, it is simply linear forces. We're not going to consider any moments of inertia or any kind of rotation in this particular case. So our acceleration, we're going to be taking as being in the negative direction. Might as well assume it as such. That's mass times acceleration, and once again the up direction is positive. So we sum the forces, and that's going to be equal to, in this case, negative ma, since our direction up is positive and we're assuming this to have a negative acceleration. We'll have negative fs minus fg minus fd equals negative ma. And since that's all negatives in there, you might as well just cross out the negatives. So this is basically our whole dynamic equation. Let's take a look at the individual components of this. We have the force in the spring. We have the force of gravity, which we already know is going to be equal to mg. And we have the force in the damper. And one thing that we want to consider above all else is the equilibrium condition, which I'm going to do over here. Because it's at equilibrium, by definition, the acceleration has to be zero. Therefore, this is supposed to be minus because the force of gravity is in the negative direction. So basically, the force in the spring and the force in the damper in the equilibrium position has to be summing to zero. And since we're taking our linearization, or we're taking our equations about the equilibrium point, we should at least include that just to show that indeed the weight force on the object is not going to affect the final dynamics of the system. So the force in the spring, first we'll consider the equilibrium condition, where we have a y naught, and we need to consider that y naught is once again in this direction. So force in the spring so we're just going to consider a y naught term in our spring and damper force. So for the spring, we're going to have the spring constant k. Since this is a linear spring, it's going to be k times the extension in the spring. And we can note here that if x is in the positive direction, that this spring is going to be under tension, and therefore the force is going to be the downwards direction. So x and spring force are in opposite directions. This will be negative x. And just in case u does move, it's not supposed to, but we're going to include it in the dynamics anyway. If u moves in the positive direction, our spring is going to be under compression, and therefore the mass is going to be feeling a positive force. So u and the force in the spring are positively related to one another. And we're also going to add plus k, and we'll call it y naught. And for the damper, this is going to be very similar. Once again, positive velocity in this case, x dot, or in this case we'll call it v for velocity, plus u dot. U dot means that it's a derivative taken with respect to time, plus c y naught dot. So at equilibrium, we're going to have ma equal to 0. And that's going to be k times negative x plus u. At equilibrium, this is going to be a 0 term, plus k y naught, plus the force of gravity, mg, plus the force in the damper. That's going to be c negative b plus u dot. Once again, at equilibrium, this is 0 plus c y naught dot. So therefore, k y naught plus mg plus cy naught dot equals 0 at equilibrium. So this basically tells us that once the system is at our equilibrium point, that we're taking everything x is being taken about this equilibrium point. Once we're at that equilibrium point, there's no contribution to acceleration from the weight and from the initial extension in the spring. So essentially, this term is going to be 0. And so once we plug this into the full dynamic equation here, ky naught plus mg plus cy naught. And those terms are going to cross out with each other to become basically a 0. Therefore, mass times acceleration equals k u minus x plus c u dot minus v. And we're going to change notations here. Our acceleration, we're going to redefine that as x double dot, or basically the dot is just denoting a derivative with respect to time. Therefore, acceleration is the second derivative with respect to time of our position x. And similarly, v is simply x dot, and that way we have everything nice and neat within the equation. So mx double dot plus cx dot plus kx equals ku plus cu dot. And the reason that we're rewriting it this way, we have a negative x, we have a negative b, I'm just bringing those over to the other side. That way we have x on this side and u on this side. So now we have the equation representing the dynamics of the spring mass damper system. What we're going to do now is we are going to find out the dynamic response of this system based on these variables. Now there's two ways that we can do this. We have the Laplace transform, or we have the state space representation. And we're going to find that these will both give us the same answer, they just apply the mathematics a little bit differently. So we'll start with the Laplace transform. We have a function in terms of x and u. And in this function, both x and u have a derivative taken with respect to time. So when we do the Laplace transform, we're going to basically set the derivative with respect to time as being equal to variable s. And that's basically what the Laplace transform is for a system that's represented such as this. So we have ms squared, that's the second derivative with respect to x, times, we're going to call it capital X because the Laplace transformation is not actually the same function as the original dynamic equation, so we need to denote this as being different in some way. To that, we're adding cs times capital X plus k times capital X. Each term in this on this left-hand side has had the Laplace transform applied to it, therefore they are all capital X. And this is equal to k times capital U, again we're doing that Laplace transform, plus c times s times capital U. And the beauty of the Laplace transform is it allows us to basically separate each of these variables from this derivative. So this capital X, we can collect like terms now, similar with the capital U, and we end up with capital X times ms squared plus cs plus k equals capital U K plus CS. And what we're going to do is we're going to represent this system of equations. We're going to represent this dynamic system as a transfer function. Something called a transfer function, which is basically the capital X over capital U. This is basically our dynamic system divided by our input. And that's equal to. And so when we go to figure out the dynamics of this system, such as the natural frequency, the damping factor, what we're looking at is we're looking at the roots of the bottom of the system. That's where the interesting things are happening. We can find the roots of the top equation here, but those won't be very interesting in this case. So we're going to just find the roots at the bottom of the system. That's going to inform us as to the dynamics of the actual problem. So continuing with the Laplace transformation here, let's find the roots of this bottom equation. Basically, M, C, and K are known values. Those are going to be basically given to you. To find the roots, we need to solve a quadratic equation. S squared plus ms squared plus cs plus k is a quadratic equation, which we can just use the quadratic formula for that. And that's basically the definition of the roots of our system. Those are the roots of the transfer function on the bottom there. This is going to define the dynamic motion of the system, and we'll see just how it does that in a moment. But first, we're going to go back here, and we're going to take a look at the state space representation to show how it gives us more or less the exact same thing. So on the state space representation, we need to define what our states are, what we're trying to represent. So we're going to define two states. That's usually one state less than what we know. So we know X, we know V, and we know A. We're going to define two states that are going to be represented here. And the easiest ones to select are going to be X and X dot, where we know that X is basically equal to itself, X dot is equal to the velocity. And so when we go to do a state space representation, the usual form for that is going to be B dot equals some system matrix A times a column vector of your states. So basically the derivative of the states, or the time derivative of the states, is going to be related to some system matrix times B. And essentially what we're getting here, a vector representation of the individual equations, or a vector representation of a system of equations. So we plug in our states here, X dot, and finally X dot dot, or it could be V dot. It's going to be equal to some matrix times a column vector of our states, X, X dot. And because we've defined an input as U, we're going to say plus some vector U. And exactly what U is, we don't necessarily need to define that at this point for the state space representation, although if you wanted to, the dynamic equation is right here. You're basically just making sure that these enter into the appropriate part of the equation, of the vector equation. We know that X dot equals V. So let's just ignore this U entirely. We're just focusing on the system matrix for now. X dot equals V. So if we're multiplying a matrix by a vector, we're basically doing a dot product of the column with the vector. So 0 is going to be our first term, because 0 times X, the X does not actually appear in the X dot term, but the X dot term appears in the X dot term once. So 0, 1 is our first column. Next we have X double dot, and here's our equation for X double dot. If we rearrange this equation, let's write it down here, so we can plug this in directly here. X double dot is 1 over m times negative c. That would be negative k over m times x and negative c over m times x dot. So we're just going to be interested in this system matrix. What we're looking for is the dynamic response of the system. This system matrix is a linearized representation of the dynamics of the actual system. So if we want to find the natural response of the system, what we're going to be doing is we're going to be finding the roots of this matrix, which, from vector calculus, actually means we're going to be finding the eigenvalues. Now this is just how we find the eigenvalues themselves. The actual eigenvalue problem is something more to the tune of a times some vector equals eigenvalue times that vector. But we're not actually solving the eigenvalue problem, we're just solving this determinant. Therefore, we're solving the determinant of our system matrix minus lambda I. So that'll be minus lambda 1, negative k over m, and negative c over m minus lambda. And when we go to solve this determinant, it's just these two cross multiplying. I will have negative lambda times negative c over m minus lambda minus negative k over m. So this minus and this minus are going to cancel out. We're going to get positive lambda squared once we multiply this through. Negative and a negative becomes a positive. It's going to be plus c lambda over m, and then this is going to be plus k over m. And we're setting this determinant to be equal to 0 to find the roots of the system. So therefore, lambda squared plus c lambda over m plus k over m equals 0. And this is very similar to the bottom equation that we had when we did the Laplace transform. In fact, we expect the roots to be exactly the same, otherwise physics doesn't make sense. So both ways that we do this, we're going to get the same roots, we're going to get the same dynamic response, because these are both essentially the same linearized representation of the dynamics of that system. So we could replace lambda with s, and we would get the same roots that we got here. So let's just bring that down here. S equals, we can see that the mass does enter into the dynamics, however the weight force that we had to consider before is not in the equation at all. So these are the roots of the system. We don't have any numbers to this yet, so this doesn't actually tell us anything. But let's take a look at a couple of possible cases that we might have to consider. So the first case we're going to be considering here is the case where c equals 0. Which basically means that this system has no damping. If c equals 0, then s equals simply plus or minus 1 over 2m times the square root of negative 4mk. And since m and k, by definition, have to be positive values, this is going to be purely complex solution. So it's going to be equal to plus or minus. This 2 is going to cancel out with the 4 inside. This m is going to be canceling out partially with the m inside, and it's going to divide. Once we square this, it'll end up inside of there. This negative we're going to take out, so it's going to be negative square root of negative 1. Or sorry, it's going to be the square root of negative 1, which is going to be I, multiplied by the square root of, in this case it's going to be k over m, which is basically km over m squared. This basically just tells us it's a purely complex root. It's a purely complex root, that means it is in oscillatory response. And as we noted before, our c is equal to 0, so that means that there's no damping. So if we were to plot this out, we're going to have an upper value, we're going to have a lower value. They're going to be equidistant from the equilibrium point. And if we have an initial disturbance to the system, it's basically going to continue undamped for infinity. Let's take a look at a second case here. In a second case, we're going to have 0 less than c squared, which is less than 4mk. So if we have our value of c somewhere between 0 and the square root of 4mk, then when we take a look at our roots here, c squared minus 4mk is not going to be completely canceled out, but it is going to be negative. And since this is a positive value, c, by definition, c has to be a positive value. So when we plug it into here, this is going to be a negative value. So therefore, our roots are going to look something like this. It's important to note here, this is going to be negative. And since this is going to be negative, we're going to have a complex root. So s is going to look something like a plus ib, which is a complex number. Since it's going to be a complex number with a real component and an imaginary component, then basically we are going to have an oscillatory response, but we're also going to have an exponential response. Now, in terms of what this is going to look like, there are a few possibilities. We could end up with something that's unstable. We could end up with something that's stable. And since we have an oscillatory response, it's going to be between the upper and lower bounds. However, in this case, we happen to know that our real component is going to be negative. And since our dynamic response is an exponential response, e to the negative anything is going to be an exponential decay, as we see here. So basically the motion is going to be getting closer and closer to that equilibrium point. So we can more or less ignore the red solution, as the blue solution is the only one that actually matters in this particular case. However, it is important to note that in some systems you will have a positive real root, which is going to be associated with an unstable mode. Let's take a look at a third case here. A third case is where c squared equals 4mk. And let's get our root in here. If c squared is equal to 4mk, then our square root is going to be equal to 0. So s equals negative c over 2m, or negative 4mk over 2m, which is just equal to negative 2k. Basically, what this tells us there is only a real component to the solution. And therefore, if we try to plot this, since it's real and it's negative, the initial disturbance, it'll just be an exponential decay to 0. And finally, we have one somewhat interesting case, which is going to be where c squared is greater than 4mk. It's going to result in a root that looks like s. This is going to be real, and this is going to be real. So depending on the state that it's starting at, you can determine what state it's going to be based on your eigenvector. If it's going to be an initial velocity or if it's going to be an initial displacement, you can determine essentially which response it's going to take, whether it's going to take the positive or the negative from this root. But what you're going to see is something similar, an exponential decay. And again, depending on which state is the positive and which is the negative, the positive state is going to decay much slower than this case, than our case 3. If it's the negative root, it would decay a little bit quicker. And again, you can figure that out using the states defined by your eigenvector if you were to find the eigenvector. So we can classify these 4 cases. The first case is completely undamped, which basically means there's an initial disturbance and it's just going to continue that way for infinity. Case number 2 is underdamped, which means that the motion does decay over time. However, it's not really instantaneous. It oscillates a few times before it does decay. We have a third case, which is critically damped, which means that it decays without any oscillation. And then we have the fourth case, which you can mostly guess it's going to be overdamped. Basically means you have this initial disturbance, it's slowing down, but at a lower rate than what you would have at critically damped. Now the fast decay that you have here is most likely going to be a velocity as the initial disturbance. But again, if you were actually doing this problem, you would find the eigenvectors to determine which root corresponds to which decay. These are the 4 cases that we have to consider. Now so far this has been rather abstract. There hasn't been any actual concrete problem solving just yet. So let's define a problem. We'll say we have a mass equal to 10 kilograms. We have a spring constant, K, of 5 newtons per meter. And we have a damping coefficient for a linear damper equal to 2.5 newton seconds per meter. Now for this particular problem, we're not going to define our free body diagram, our mass acceleration diagram. We've done that above. We got our x double dot equals everything. We've defined the roots already. We're just going to use these roots directly because this system is exactly the same as the one that we just derived. So our roots are going to be as follows. If we plug in the values to this equation here, so basically this tells us that our eigenvalue has a real component that is negative and an imaginary component. So if we want to find the natural frequency of this system, we need to consider both, that these both have an effect on that dynamic response. And our natural frequency is incidentally the magnitude of the complex root. So the magnitude of this complex root is going to be a squared plus b squared. You take the square root of that, 0.125 squared plus 0.69597 squared. That's going to be equal to approximately 0.7071. Approximately. Next, we want to define the damping coefficient. The damping coefficient can be defined as the real component a divided by the magnitude of the root, so a plus b squared, both squared. And that's going to give us, our damping coefficient is going to be negative a. Sorry, I forgot the negative sign in there. This is going to be negative 0.125. You can see why I forgot the negative sign there, because it's going to cancel out anyway. Divided by the square root, well in this case we know what the answer is, it's omega n, because that's what this was defined as, so 0.7071, which is going to be approximately equal to 0.1768. And finally, we want to define the actual equation for the dynamic response, x as a function of time, given an initial disturbance. We know that from mathematics, given the form that the initial equation took, the x double dot plus x dot x, right? These are all time derivatives. We know that the form of this is going to be something similar to a e to the first root s1 t, b e to the second root s2 t. We know that there's going to be 2 roots because there's second order. because this is a second order linear differential equation. So therefore, we can write this out a little bit further. What we're going to do is we're going to explicitly define our root here. So S1 equals and S2. We're going to also define this as being equal to A plus BI and A minus BI, such that we can write this equation out in a little bit more simpler terms. X of t equals A e to the power of A plus BI times t plus B e to the power of A minus BI t. And when we go to expand this from our complex variables, we know that e to the I is going to be sine 1 plus, it's going to be cos 1 plus I sine 1. But since we have this I multiplied by b, it's going to be cos b plus I sine b. In both cases, although it's going to be negative for this one, as the roots happen to be conjugate in this case, that's going to be equal to A, because in this case b is the negative conjugate, so we have to make this a negative sign. For cosine, we can put a negative inside of the cosine, it's still going to be a positive cosine. So let's expand this a little bit. These both have an e to the at term. And this gives us another interesting result. We can note that A plus B and A minus B, those are both, once again, conjugates. And we can also note that both sides of this equation are offset by 90 degrees. We have a cosine, we have a sine. Those are offset by 90 degrees. So let's define A and B. Let A be equal to some complex number, k1 plus I k2, and we'll let b equal to the conjugate of that same complex number, k1 minus I k2, which basically tells us a plus b equals 2k1, a minus b equals 2I k2. And again, these are arbitrary numbers, but we see here that these are offset by 90 degrees. Since one of them is real, the other one is complex. So we can take this result, plug it back into the equation. So we're going to write out our equation here. We'll plug in A and B. This is what we end up with. So we need to note that A plus B, that's 2k1, that's what we got there. A minus B is 2I k2, we multiply that by the I, what we end up with is negative 2k2, and that's there. And let's further simplify this, we'll bring that 2 out in front. Now, we're going to redefine k1 and k2. k1 is going to be some constant k multiplied by sine phi, and we'll let k2 be some constant k multiplied by cosine phi, which, since these constants are both arbitrary, we can get rid of that 2 out in front and just replace it with the k, which basically takes care of any constant multiplier. Multiply that by e to the at, all multiplied by sine phi cosine b minus cosine phi sine b. Now, another important thing that we should probably note here is when I did this expansion here, this value of t is still multiplied by b. This cos b is, and sine b, these are all multiplied by time. So knowing our rules of sinusoidal functions, we can simplify this one step further by making this sine and in this case it's going to be negative bt. And again, basically what this tells us is we have our magnitude, we have our exponential response or decay, we have our oscillatory response, and we also have a phase shift, which basically tells us that if the function is rotated by any number of degrees when it starts. So if we wanted to plot this, let's say we have an initial response of x naught, or x of 0 equal to 10. So at time t equals 0, we're going to have t equal to 0, so this exponential is going to be 1. It's going to be sine of 0 plus phi. We can basically determine that this has to be equal to 1 because it's the initial response. Our k value is going to be equal to 10, so there's 10 right there. And this value of phi is most likely going to be 90 degrees. So we're going to plot this response. Now if we wanted to plot this for however many cycles there would exist, we need to consider our time constant, which I'm actually going to rewrite this equation down here. We're going to have 10 e to the negative 0.125 t multiplied by sine of negative 0 plus, in this case it's going to be plus 90 degrees in order to get us at this starting point. And that's our equation for x of t. Now interestingly enough, if we want to figure out how long it takes for that motion to decay, we need to consider this exponential decay. So for exponential decay, for 98% of the motion to be completed, we need to be at approximately 4 time constants. And what's a time constant? Well, an exponential decay is defined as e to the power of t over tau, where tau is a time constant. Well, that's essentially what we have here. Sorry, that would be negative t over tau. That's essentially what we have here. 0.125 is 1 over 8. So in this case, we have an exponential decay with a time constant equal to 8 seconds. So once we have 4 times 8 seconds, or about 32 seconds, that's when we have 98% decay of the motion. We also have this oscillatory response, which if it's going to be 32 seconds, we can calculate how many radians of rotation that's going to be. 22.27 radians, that's also going to be equal to about 3.5 full oscillations. So basically it's going to go up, it's going to start up, it's going to go down, and then come back up about 3.5 times before the entire motion has decayed. So let's draw this out here. Which, as you can see, more or less keeps in line with that exponential decay. If we were to continue drawing this, we would see it continue decaying as it goes down the line, and once we get to around 32 seconds, then we would have it decayed about 98% of the motion. So that's that is the characteristic problem of control theory, and the characteristic application of differential equations. Specifically, this one is of the second order. And basically, this just gives you an idea of the dynamic response of a spring mass damper system, which, interestingly enough, occurs in more places than you would imagine. So that's the spring mass damper dynamic response, along with an example there. If we wanted to, we could calculate the damping coefficient of these four cases. If you want, you can derive that yourself. You just have to plug these variables into your damping factor formula, A over square root of A squared plus B squared. And you have both of these. You can just plug those in directly there and you get the damping coefficient. Anyway, I am Arlington Matrix, and that's everything for today. If you have any questions, feel free to leave them in the comments section below. I understand this was a little bit of a rushed, maybe a little bit convoluted example. If you do have any questions, I'd be happy to either respond in the comments or make a new video with further explanations. Thank you for watching. Please subscribe and have a great day.